Stable Diffusion, DALL-E, and Midjourney all use diffusion models. These generative models work by learning to reverse a gradual noise addition process, starting from random noise and progressively denoising it into a coherent image. In the next few minutes, we will explore the elegant mathematics behind this approach, the key architectural components, and how diffusion models power the AI image generation tools transforming creative industries today. Let us get started. Let us understand the core mechanics of diffusion models and why they produce such remarkably high-quality images. Diffusion models learn to reverse a noise addition process, progressively recovering coherent structure from pure randomness through a sequence of learned denoising steps. Let us define the core vocabulary for understanding how diffusion models generate images. Denoising is both the training objective and the generation mechanism of diffusion models. During training, the model learns to predict the noise that was added to a clean image at each step of the forward corruption process. This prediction task, while seemingly simple, forces the model to develop a deep understanding of image structure, composition, and semantics, because accurately predicting noise requires accurately understanding what the underlying clean image should look like. At generation time, these learned denoising predictions are applied iteratively in reverse, progressively refining random noise into a coherent image that reflects both the model's learned understanding of images and any conditioning information provided. The latent space is the compressed representation in which modern latent diffusion models, like Stable Diffusion, operate. A variational autoencoder is trained to map high-resolution images into a much smaller latent representation, typically reducing spatial dimensions by a factor of 8 while preserving the essential semantic and structural content. The diffusion process then operates entirely within this latent space, which is computationally far less demanding than operating in pixel space. After generation is complete, the decoder component of the autoencoder maps the final latent representation back to a full-resolution pixel image. This compression-diffusion decompression architecture is what enables high-quality image generation on consumer hardware. The guidance scale is a critical hyperparameter that controls the trade-off between prompt fidelity and image diversity in text-conditioned diffusion models. At a guidance scale of 1, the model generates images based purely on the statistical properties of its training data, largely ignoring the text prompt. As the guidance scale increases, the model increasingly biases generation toward images that match the text conditioning. At very high guidance scales, above 15 or 20, images strongly reflect the prompt but become less photorealistic and more stylistically exaggerated. Choosing an appropriate guidance scale is part of the art of prompt engineering for image generation, and different subject matter often benefits from different settings. Stable Diffusion is the model that democratized text-to-image generation by making a high-quality latent diffusion model available as open-source software in August 2022. Its release was transformative because it ran on consumer GPUs with as little as 4 gigabytes of VRAM, hardware accessible to millions of users rather than requiring data center infrastructure. The open-source nature of Stable Diffusion also enabled an explosion of derivative models, fine-tuned variants, extensions, and creative tools built on top of it. Understanding Stable Diffusion's architecture, latent space operation, U-Net denoising, clip text conditioning, and classifier-free guidance provides a foundation for understanding the entire ecosystem of modern image generation tools. Now let us see where diffusion models are creating the most significant value across industries. Diffusion models are transforming creative workflows, product development, and content production across industries. Let us close with the 4 most important lessons from this overview of diffusion models. To explore more key concepts in generative AI, check the link in the description. If you found this helpful, please like and subscribe. Thank you for watching. If you found this helpful, please like and subscribe. See you in the next video.